Alright, this video overviews homework assignment 4 for Introduction to Parallel Algorithms. This homework assignment basically is an extension of homework 1 where we parallelize it using OpenMP. So just for a brief review, homework 1 essentially was creating a very large array of random numbers and then computing the standard deviation. And then after that's done, we smooth the array by taking an average of the neighboring values and calculate the standard deviation again, and iterate that and watch as the standard deviation goes down. So this assignment uses OpenMP to parallelize that, so it can observe a speed up for very large arrays. So first up, here we have our function prototypes right here. This function generates the random array of a set size, and it does that in parallel using this parallel section right here, and then it has right here private, so each parallel region has its own local RNG state. Next up, here we just calculate the sum, so we define this double S, which will be our sum value, and we use the parallel for loop to just calculate an accumulating sum of that S and then return that value. Next up, we have the standard deviation using two parallel reductions. First of all, we have to calculate the mean using this parallel for loop, which, similar to the sum, it calculates an accumulating total of the array values, and then after that it divides it by the size of the array to get the mean value. Once we have the mean value, we can calculate the standard deviation, currently defined as var for variation. So we can calculate the standard deviation in this parallel for loop by this formula, and then after that we return this value is the standard deviation, the square root of r. After that, the last function we have is the smoothing function. So essentially what this will do is it takes in a weight value, which is how strongly they'll be averaged with the neighboring values. And first of all, just if it's less than 0, if it's greater than 1, it just sets it back to either 0 or to 1 if it's outside the range. So first of all, we have to make a temporary array, and we set the end value, so the 0, and then the end value of it to be the actual array's values. And then here we have our weight, W, and then we have 1 minus W because we used that in the formula. Next up, we have this parallel for loop, which goes through and assigns each index of the temporary array to be this formula, which just calculates the smoothing according to the actual array that we have. So once that is done, we go into this next parallel for loop, which assigns the actual array the values of the temporary array, and after that is very important, we have to free the temporary array so it doesn't keep taking up memory after the program is run and accumulating all of that and slowing things down. So that's all of our functions. Here we move into the main. Right now, the size of the array can be taken as a user input when it's running the script, but for right now it's just set to a very large default value, so we can see the scaling. So it's very slow for a low number of threads and gets faster for a larger number of threads. Next up, we have the iterations. Again, this can be taken into as a user value, but right now it's just set as 8 as the default. After that, we just make a random number seed for that, output some stuff to the terminal, and once we have that, move in, make this A, and then after that, once that is done, we make the random array and we time it, and then we output the time that it takes to make that random array, since that will depend on the number of threads as well. After which we calculate the standard deviation of the array, time that as well, and then we'll output that once that's done. Next up, here we have this loop, which will iteratively smooth the array. So first up, it times the smoothing, or it sets up a time for the smoothing, smooths it, and then records that time. And then it also takes times how long it takes to get the standard deviation of the array, and then it just outputs those to the terminal. And that'll be done on a number of iterations, so we can see as the iterations progress, the standard deviation will be decreased. So once that's done, all we have left to do is free A, and then that's all we have. So I'll pull up some results that I have for this. So here I tested a different number of threads, and I recorded the standard deviation time and the time it took to generate the random numbers. And we can see that both do go down from one thread, so just serial execution. They go down, it roughly halves, the time it takes roughly halves whenever we double the number of processors. Up until about 32, this is the last place that we really see improvement. From 32 onward, the standard deviation time stays pretty much the same, all the way up to 256 threads, which is the max that I tested. And then after 32, we can see that the time it takes to generate the random numbers actually starts to increase again. So with 256 threads, it takes almost the same amount of time to generate the random numbers as it does for using 8 threads. So we can see that 32 to 64, that's around the most optimal number of threads in terms of time. Now that is only for this array of this size, which I'll go back to the tab. So right now we're setting the size as 20 million. So if that were to change, then I'm sure that this time plot would change as well, though I expect the trend to be more or less the same. So that's all there is for this assignment.